Find the force exerted by each cable to support the 625 newtons bag in figure 4-32.
Find the force exerted by each cable in this figure, in the angle is 37 degrees, right? Okay. It says we have a 625 Newton male bag suspended, as you can see via the figure. 625 newtons refers to what about the bag? 625 newtons. Andrew.
That's how much gravitational acceleration or something is exerted on it.
Gravitational acceleration or something. Can someone clarify? House.
The force of gravity.
It's the force of gravity. It's the weight of the object. It's the same thing as saying I'm a 150-pound person, right? It's a 625 Newton bag. So that is the force of gravity existing on the male bag here. The force exerted.
Teachers, the tardy sweep is complete. Students will be returning to your classrooms in 2 minutes. Thank you.
I don't know.
Maybe you get his attention because Jeremy tried to get me, but
I don't know.
yeah.
It's not my job. This is my job. Force exerted by each cable the force exerted by a cable has a specific name. Mitch, what is the name of the force exerted by a cable?
Force applied.
No, the force applied is not the force exerted by a cable. That would be the push or pull by a person or an object. Wheatley.
Tension?
The tension force. So the question is, what is the tension in each cable? We have drawn our picture. We've listed our knowns. We know we're looking for the tension force exerted by each cable. We know this has to do with forces. Therefore, what should we do next, Brian? We've drawn a picture. We've listed everything we know. We know we're trying to find forces. Therefore,
I'm having trouble.
you're having trouble hearing Nick?
No,
Is that the issue?
I'm really not sure.
Who wants to help him out? What should we do next? Andy?
Well, are those like dashed lines?
Those are like
walls?
a wall. Yeah. What should we do next? Nick?
Free body diagram.
We should draw a free body diagram. Anytime you're dealing with forces, you should draw a free body diagram. Rather than drawing it right here, I'm actually going to draw it over here. So this dot right here is the same as the dot right there, but rather than muddling things over on this side, we're just going to draw it right there. So give me a force in our free body diagram, please, Lily.
Gravity. Of the force of gravity, which is 625 newtons.
Down, there we go. In order for me to draw it, I have to have a direction. So the force of gravity, I agree, is down. And we generally don't put the numbers in our free body diagrams. We just put the symbols. Force of gravity is down. Give me another force in our free body diagram, please. Connor?
Force normal, which is up.
Force normal. Force normal, by definition, what is the direction of the force normal, Connor?
Perpendicular to the surface.
And?
It's always a push.
Always a push. Perpendicular to the surface and always a push. To which I ask the question, what surface? Right? Is there a surface acting on the mailbag right now? No. So is there a force normal? In the absence of a surface, there is no force normal. In the absence of a surface, we can't have a force normal or a force of friction. It is very common for people to just want to add a force normal in, but you need to realize you cannot have a force normal if you do not have a surface. Other forces in our free body diagram. Headline.
Tension from the ropes.
Give me one tension force, which direction?
There's one going that direction.
Okay, that direction, as you indicated, will go this way. We'll call this one tension 1.
Is it like 63 degrees?
Once at an angle, we'll talk about the angle. It's in the direction of this rope. Okay. Good? What other force do we have? Christine. Say again? Give me a direction. You can just point. It's usually the easiest way to do it. That way, to the left, in the direction of the cable. We'll call this one tension 2. So we have tension 1 and tension 2. We have the force of gravity. If you look here, we have, if I draw a parallel line to the ceiling there, we can draw a theta. Note these two thetas are the same because of alternate interior angles. Is that true?
Yes.
Okay. Therefore, this theta right here is going to be our 37 degrees. We have drawn our free body diagram. Mario, what should we do next? I think I should lecture this.
Watch you.
Mario, I can't see.
With her given.
We've already listened to it. Other ideas?
I'll break it into
Yeah. What's it?
break it into its components.
What's it?
Break into its components.
An unidentified antecedent, it, has no antecedent. What's the it?
Tension.
Tension 1. So we need to break tension 1 into its components. Oh! Tension 1 in the x direction, tension 1 in the y direction. I'm sorry, Mario, I just have a really hard time when people speak, so please, people speak so that we can hear you. Meredith.
Did you ask me something?
I did. Could you please break tension 1 into its components?
I don't think we know tension one.
Oh! We don't know tension 1? Ye gads. What do we do, people? Meredith.
Can you make like from tension 1 to the force gravity? Would that create a triangle?
We have a triangle. You can see a right triangle right there. We have one with tension 1. We don't, right, we need to find tension 1. But we don't know tension 1, do we, Brian?
I think we do.
We don't, actually. She's right, we don't know tension 1. Sorry, Brian. We will find tension 1 eventually, Andy.
So like what she said, if you take the tip of tension 1 and you draw a triangle to force.
We're not going to create more triangles. We already have a right triangle. We have everything we need. But unfortunately, we also have something we do not need, which is a numbers dependency. You all have a numbers dependency. Meredith just said to me, I can't break tension 1 into its components because I don't know tension 1. Just because you don't know it doesn't mean you can't break it into its components. So you need to let go of your numbers dependency. I will help you let go of your numbers dependency slowly but surely. Here we go, Meredith. Please break tension 1 into its components.
So sine theta equals opposite over hypotenuse.
What is opposite theta?
T1y
T1y over hypotenuse.
over the tension 1.
Tension 1. Therefore, tension 1 in the y direction equals tension 1 times the sine of theta. Class, do we know tension 1? No. Do we know theta? Yes. We could plug in theta at this point, but that would just be stoking our numbers dependency, which we are not going to do. Instead, what we're going to do is we're going to say, we can't go much farther with this. So we're going to put it right here, which is, we're going to put it in the equation holster. Just in case, at any point, we need to pull it out and use it. We do the same thing with cosine. Cosine theta equals adjacent over hypotenuse, where we have tension 1 in the x direction over tension 1. Tension 1 in the x direction equals tension 1 times a cosine of theta. So tension 1 in the x direction equals T1 cosine theta. Again, we don't know either of those, so we're going to put it in our equation holster. We have drawn our free body diagram. We broke tension 1 into its components. We are now going to redraw the free body diagram for clarity's sake. So we have still the force of gravity. We still have tension 2. We now have, instead of tension 1, we have tension 1 in the y direction and tension 1 in the x direction. we have drawn our free body diagram. We broke the tension into its components. We redrew the free body diagram. We are now going to use Newton's second law. We are going to sum the forces. Jessica, which direction would you like to sum the forces in? All right, if we sum the forces in the x direction, Jessica, look at our free body diagram. Tell me which forces are acting in the x direction and whether they are positive or negative.
Positive tension 1x minus tension 2.
That is equal to, according to Newton's second law, what, David? David, tell me what's Newton's second law?
The sum, the net force equals, I have no idea.
This saddens me. Saddens me to no end. What are you going to do when you're stranded on a desert island?
Swim.
So sad. Sam, help him out.
It's mass times the acceleration.
What is the acceleration in the x direction of the mail bag? Knickerbocker.
Zero.
It's not moving at all, right? So the acceleration in the x direction is going to be equal to 0. So we have t1x minus t2 is equal to 0. In other words, t1 in the x direction equals tension 2. What now? Nicola.
Sum of the forces in the y direction.
We will do that shortly. There's one thing I want to do first. I agree. We're definitely going to do that after this. Meredith?
What the equation holster thing is T1x.
We are going to remove from our equation holster t1 in the x direction equals t1 times the cosine of theta. We now have t1 times the cosine of theta equals tension 2 from our equation holster. Now, we're going to sum the forces in the other direction. As of yet, we still haven't found any numbers, but don't you worry, we can put this in our equation holster. We can sum the forces in the y direction. Please look at the free body diagram and sum the forces in the y direction. Christina?
T1y minus FG.
What does FG stand for? Which is then equal to the net force in the y direction? Net force in the y direction is going to be equal to what goes right here.
0.
Not quite. We need an equation. Don't worry. David's going to get it for us. David?
Mass times velocity in the y direction.
Mass times what?
Velocity
Velocity in the y direction?
y or x.
Sam, help David out again.
It was mass times acceleration in the water.
Mass times the acceleration in the y direction. What is the acceleration in the y direction of the mail bag here? Lily? 0. No, the bag of mail is not moving at all. So the acceleration in the y direction is going to be equal to 0. T1 in the y direction minus the force of gravity equals 0. Therefore, the tension 1 in the y direction equals the force of gravity. Meredith.
When you substitute in the 625 and the T1 y, you get T1.
Bless you. Well, let's substitute for t1 in the y direction. What's that? Hong?
It's tension 1 sine theta.
From our equation holster, we know t1 in the y direction equals t1 times the sine of theta. That's equal to the force of gravity. What is the equation for the force of gravity, Emma?
Mass times acceleration.
Very close. the equation for the force of gravity. Mitch? Mass times the acceleration due to gravity. Mass times m times g.
Okay.
Who can explain to me why we're not going to substitute in m times g, however, for the force of gravity right here? Why aren't we going to substitute in with that equation? Joshua? We already have the force of gravity. At this point, we don't need to substitute in because we have the value, as Meredith told us, at 625 newtons. So we now can figure out tension 1. It is simply equal to the force of gravity divided by the sine of theta, or 625 divided by the sine of our 37 degrees. Tension 1 equals. I'm sorry, 5251. So tension 1 with 2 sig figs is 1.0 times 10 to the third newtons, or 1,000 with 2 sig figs. We can now solve for tension 2. Going back to our equation holster, we have tension 2 then is equal to tension 1, 1038.5251 multiplied by the cosine of 37 degrees. Tension 2.
829.403.
Okay, tension 2 then with sig figs, 830 newtons. What we just went through is a standard recipe for solving problems with force. Step 1, draw the free body diagram. Step 2, break things into components. Step 3, redraw the free body diagram. Step 4, sum the forces in one direction. Step 5, sum the forces in the other direction. Let us review. This is the standard recipe for solving problems with force. If you take my AP class, you will find that you are going to be using this for approximately the next 2 years in physics. Step 1, class. We'll try that again. That was exceptionally poor. Step 1, class. Free body diagram. Step 2. Step 2 is to break forces into components. We'll try again. Step 1. Step 2. Fair enough. Step 3. Redraw the free body diagram. Step 4. How's it going, Andy?
Great.
I don't hear a whole lot coming from over here. Step 4, class. Step 5.
Circle your answer.
Step 4 and 5 seem to be the same. They are both sum the forces, but realize you're summing the forces in one direction, and then you are summing the forces in the direction that's perpendicular to that direction. So in this case, the x and the y direction. So again, draw the free body diagram. Break into components. Redraw the free body diagram. Sum the forces in one direction, sum the forces in the other direction. It's going to happen many times.